Hello, welcome to my talk, Learning by Taking Things Apart. I'm going to talk about how container images are made. And I'm going to show a tool that I think is really cool called BuildKit and teach you about compilers. Also do some code demos and talk about the future of containerization. And the big takeaway that I hope to give everybody is an intuition about how containers are created and show you some things that maybe you didn't know were possible. So the idea for this talk came when I was presenting at a meetup. I was talking about containerized continuous integration and Earthly, this open source build tool that I work on. And someone asked a question about the way containers were created. Not the external commands that you call, like Docker build, but the actual mechanics of creating a container, like what are the steps and what happens. And I didn't really know, but now I do. So that's the thing that I want to talk about today. About me, I'm Adam Gordon-Bell. I'm a software engineer. I am a developer advocate at Earthly. I like compilers and dev tools. I have a podcast about software development and what else? I'm Canadian. That's probably enough. So a little background before we jump into it. I'm not going to be talking today about running containers, like when you do Docker run and start up a container or whatever happens in Kubernetes. I'm going to be taking a step back from that, talking about a step before that, the step where you're actually creating the container image. Do you know the difference between a container and an image? So the way I like to think about it is by analogy. An executable is like a program you run on your computer. When you launch it, it becomes a process, and you can launch however many processes you want from that executable. Similarly, an image is something that's not running. When you run that image, it becomes a container, and you can run as many containers as you want from a single image. So an executable is to an image as a container is to a process. And you could imagine how like a virtual machine might fit in that as well. Like you can have a virtual machine image, and when you start it up, you have a running virtual machine. Except an image for a container is immutable, just like an executable doesn't change when you run it. Anyways, this analogy is going to be important as we talk about how Docker build works. So the question that I was asked was sort of this, right? You have a Docker file and you turn that into an image. Like what actually happens there? Like what happens down in the weeds? Like what are the details of turning this into something that I can run somewhere? And it turns out that that's a super interesting question. And to understand it, we have to kind of take a bit of a step back. So talking about executables, where does an executable come from? How is an executable like a program created? So here's an example C program from Dennis Ritchie and Brian Kernan's book on C. And the compiler, the program is just a simple hello world, and Clang is the compiler. And Clang is a front end for the C language, and it's part of a compiler known as LLVM. And so this is how we can build it, turning it into an executable, and then run it. So when we build that program, we get something like this. I'm compiling it to x86 assembly, and this is what I get. The assembly code maps almost directly onto machine code, which is binary and much harder to read. But machine code is what your actual CPU understands. It's the machine architecture of your CPU. And no one really does this, but you can actually write assembly code yourself by hand. So the Docker file equivalent looks like this. We have a Docker file on top, we build it using Docker build, and we produce an image. And the process is similar to how we made our hello world. Docker file is passed to something called BuildKit, which is inside of the Docker build command, along with our build context, which is a dot in this case. Generally, each statement is turned into a layer as part of this build step, and those layers are packaged up into an image. One thing that's different from a traditional compiler is that with a compiler, you're just taking in source code, but Docker builds, you're actually taking in a file system context. So in this case, we're passing in our present working directory, which is what we need to do that copying that README in. And you can actually create an image manually yourself. Each layer is just it's kind of like a zip file where the name of it is a SHA-52 hash of its contents. So you could create one yourself, each layer, and then you could make a manifest, which is what describes the image format. It's just a pretty simple JSON file describing the layers and some metadata. Once again, nobody's really making these by hand, but it can be done. So comparing our C program to our Docker building, we can see how they look quite similar. We have our container image compiler that does the heavy lifting, and we have Clang that does the heavy lifting. And the heavy lifting on the Docker side is done by BuildKit. So this is BuildKit on GitHub, and it drives not just Docker build, but a number of interesting cloud native projects. One of them is OpenFaaS, which is a project to run serverless functions on Kubernetes. Rancher Rio is an application development engine for the cloud, and there's probably a whole bunch more. Earthly uses BuildKit, which is how I kind of got involved in this whole story. And if you try to dig in, like, well, how does BuildKit work? You come up with this thing that they have in their README, which says LLB is to Dockerfile what LLVM-IR is to C. Okay, seems like we're going back to compiler. So let's dig in a little bit more on what this statement might mean. So earlier, we had this diagram of how the compiler works. And once you get into the details of what a compiler actually does, this turns out to be a little bit of a lie. On the left here is the PDP-11. The first C compiler was written for the PDP-11 by Dennis Ritchie, who worked with Brian Kernighan on that book and the Hello World example we saw earlier. But it worked totally like that diagram. The C code would be taken in by a compiler and would be converted to PDP-11 assembly instructions, which would be converted to machine code and executed. But this direct mapping poses a problem. Whenever you have a new machine, it means you need a new compiler. And what language do you write that compiler in? So the first C compiler was written in, I believe, PDP-11 assembly, but you don't want to have to rewrite every compiler in the assembly language of whatever machine you want to target, because like what happens when the VAX11 comes out, which followed the PDP-11, or the new Apple M1. These have different instruction sets, and so the assembly is different and you'd need to rewrite it. Not a good solution. So this problem was very quickly solved by the compiler authors who came up with this structure we see here. They said a compiler can be split into 3 steps. You have a front end that takes in your source and your various files, and it tokenizes them and parses them. You have a middle that is an optimizer. It does performance optimizations to make the code faster. At some point, they called this the middle end, which is not my favorite term, so I'm glad it didn't catch on. And then you have a backend, which actually generates the assembly that can be run on the various machine architectures. So now you don't actually have to make a new compiler for each machine architecture. All you have to do is make a new backend for each machine architecture. And this will all relate back to Docker builds, trust me. The trick is getting all these backends speaking the same language, right? So to do that, you need an intermediate representation. You need some way that all these backends can speak the same language, but generate different machine code. So you need a language that basically isn't C, but isn't the machine-specific assembly either. It needs to be somewhere in between. And once you have that language, all the backends need to do is translate it from it to machine architecture, the machine architecture that they need to run on. In our first C example, we use Clang, which is a front end for LLVM. And hopefully that's starting to make sense now. LLVM is a compiler that follows this 3-tier structure. Clang is a front end for it. So LLVM was created as a research project, but now it's heavily supported by Apple. So once you have that kind of structure, you can now have multiple front ends. This is what modern LLVM looks like. It started with the Clang front end, and now it has many front ends. There's been sort of a Cambrian explosion of ahead of time compiled languages that happened in the past like 10 years or so. And it's a result of it being easy to add a new front end to LLVM. All you need to do is create that new front end. Now you have a new programming language, and it can run on anywhere that there's a backend for LLVM available. And the reason for this is that this IR acts as a common interface between layers. And on the backend, a WebAssembly backend means that you can write C or Rust or Julia that can run in your web browser. And there's even a GPU backend. So maybe you can compile things down to run on pixel shaders. If you can build a front end and emit this IR, you now have a new programming language. And if you can build a new backend, then all of a sudden you can run all of these languages on whatever that backend is targeting. This is super cool stuff because the secret is just this format, this intermediate representation. It's a pretty neat little trick. So now bringing it back to container images, we can finally understand that quote. BuildKit works the same way as LLVM. It has something called LLB, which is its intermediate representation. And it has this because containers need to be able to run on a number of machine architectures. And once you have that IR, that LLB for varying the backends, you can start to have many front ends as well. Right now, obviously, the most common front end is Docker files, like we were just looking at, but that doesn't need to be the limit. LLVM IR looks like this. It looks like kind of a verbose and explicit programming language. LLB looks quite different, where LLVM is the basics of a simple programming language on the left. LLB IR is a language for creating self-contained cloud-native packages. And now that we understand the structure behind making a Docker build statement, let's play around with it. Let's see what we can do. All right, demo time. So this is the Docker file that I showed at the beginning. Very simple. We start from Alpine. We're going to copy in our README, which you can now see is over here. And then we're going to echo to a file, standard Docker build. This whole demo I'm going to take you guys through is available also if you want to play along at home. So it's on GitHub under my username, which is agbell, under compiling containers. So the first thing we're going to do is just a standard Docker build. So we're going to just build it, pass in the present working directory, and then we're going to call that agbell demo1. We build it like that, and then once we have that image built, we can run it. So we're going to run it interactively, agbell demo1, and then we will start up a shell. So now we're inside of it. We can see everything. So our README is there, right? And then our build file, we can see right there, standard Docker build. Also, like maybe we don't even have to look around inside because we can see it running right here. It prints out what it's doing as it builds the images. But, you know, sometimes it's nice to verify these things. Okay, so that's just a very simple build. Now let's build something directly using BuildKit. So to do that, we are going to install BuildKit. So the first build happened using BuildKit as well, but the Docker daemon was running in the background and had BuildKit running inside of it and used it to build it. But now we're going to use it directly. So now that we have it installed, we get this kind of build CTL program, which we can use to interact with the BuildKit daemon. And then we need to start up the daemon. The way I like to do that, because I'm on a Mac, is I start BuildKit, which has this Docker image, Moby BuildKit, as a privileged container, and I just name it BuildKit. Looks like I already have it running. And then I just need to tell buildctl where to find it. So buildctl looks at this environmental variable, so I'll just tell it that it's running there. So then once I have that in place, I can do the same type of build, except we're not going to call it a standard Docker build anymore. Let's call it a BuildKit, BuildKit direct build. Let's try that. So BuildKit, buildctl is a little bit more verbose. It has a couple more options. So here is a buildctl build. So we're going to call build. We get to specify our front end, which you might remember from that diagram, pass in our context, and then here we have kind of the back end option. So we can choose outputs. You can output an image or a tar file or whatever type of backends it supports. And then we're going to call this demo2 and we're going to push it. So we can build that and we can see here it building it. And the reason for pushing it is kind of interesting too, because now we're building it inside that container I started up. We need to like push it somewhere so that we can retrieve it and run it. So we should be able to actually pull it now, demo2, like that. And then we can run it the same way we did before. So a Docker run agbell demo2, and we'll start up our shell. And then if we look inside of our, why isn't that? Yeah, there we go. So then we get BuildKit direct build. And we should be able to see that our README is there as well. So that worked. So now we're just building it directly with BuildKit. All right, so what should we do next? So if you recall from our diagrams earlier, we were saying that this kind of three-phase architecture means that a front end communicates with BuildKit, it communicates with the middle, and it sends its results to the back end. And all of these stages are specified in terms of this LLB. Right? So one thing we can do is actually LLB. One thing we can try to do is actually send LLB directly to this BuildKit daemon. So LLB is specified in terms of a protocol buffer, and you can actually make these calls against BuildKit using gRPC. So basically, in any language that has support for protocol buffers, you should be able to write something that generates this and then send it along to BuildKit. So I built an example of this. I don't know why I can't close that. Yeah, so I built an example of this called write LLB. So here I'm using Go because Go already has nice bindings for LLB, but yeah, as I said, you could use any language you want. You can see my create LLB state is very similar to our original Docker file. We have our image specified here, then we're going to copy our README. We have to specify a context. The only stage that's somewhat different is our run statement, where because we are pushing standard out to a file, which is kind of a shell command, we have to launch a shell and then run that inside of it. But it's pretty close to our original Docker file. So to run this, we can just do go run, and then it is called write_llb.go. And then we get this nice output. So protobufs is binary format, and if you see here, we're actually just writing to standard out, which lets us see the raw LLB, but certainly not super useful. So if we want to see what it looks like in a nice format, then buildctl has a nice thing called, I think it's called dump LLB. And then if we want to format that nicely, we can pass it to JQ. And then we get this nice formatted LLB output, and we can see actually what this is generating. It's verbose, but it's all here. We can see, like, here is our run statement. We should be able to see, here's our README, so you can see the action, copy, README. Should be able to see, here's our sort of from equivalent. So that's what LLB kind of looks like in the raw, I mean, when formatted nicely. So now let's try to actually build this. So we can use similar statements as before. Let's start there. So we're going to build it, but instead of just piping it out, we're going to tell buildctl to actually build it. So we say buildctl build. Our context is present working directory, and then similar stuff to before, we're going to make it as demo3 and push that. So now, yeah, like this program is generating LLB, and we're just using this buildctl as like a helper to pipe it through to BuildKit. So now, like, if I were, if I were productionizing my little 5-line thing, I might not want to use this buildctl program. I might actually want to, see, check that environmental variable myself, or somehow know where BuildKit daemon is running, connect to it and send the stuff directly, maybe start it up if it's not there. But this works really nice, especially for a demo. So it seems like it built, right? So then, kind of similar as before, I can do docker run it. I will pull it first and spell my own name right. And I think we're on demo 3. And then let's start up the shell. See, it pulls down, and if we look at our build file, we can see programmatically built. Bam, so it worked. So, I mean, this is a really little demo, but I think this is really cool because you can use all the abstraction and control flow that that programming languages offer you, right? If you wanted to do like some sort of control flow or loops or something like that inside of a Docker file, it's not entirely clear to me how you would do that. And here you get to kind of raise the abstraction level, right? Everything that's available to you in a programming language, you can now do to generate Docker files, including using like libraries that might be available in your language of choice. So I think it's pretty neat just being able to do this. Let's move on. Let's keep going from here, right? So that was a front end, right? But it was a front end that just sent LLB directly to BuildKit. But like a true front end probably does other stuff, right? It probably like is more like a real compiler where it takes in source and it like parses it and maybe produces some errors and whatever, and then it makes the intermediate representation that it then sends through to BuildKit. So there's a bunch more layers, right? And it's actually pretty easy to build something like this with Docker and with BuildKit. So Docker has this syntax where you can say in the front, on the top line of your Docker file, you can say syntax, and then you can give an image name. And then it interprets that to mean this is a Docker image that contains the front end that I would like to have this build run in, right? So now we can have a true front end and use it, right? So to build something like this, you need to have it somewhere that Docker can pull from, but it also needs to do all these steps, right? It needs to accept text as an input. It needs to tokenize it and parse it and generate the LLB. And then, you know, the Docker build will take care of the plumbing of sending that on to the next step. So I did this. I built a trivial front-end programming language for Docker build. And it's called ikfile, and you can find it in this repository as well. So the first thing that we should do to show how it works is actually build a Docker container that contains it, so we can do this type of thing. Don't save. So I have that here. This is my Docker file for my Docker front end. So it uses Golang. It's going to copy in the source. It's going to run a build command, and then it's just going to set as the entry point the executable we're creating. So I can build this Docker build, same stuff, but now we have a different file name. So we need to do ikfile.dockerfile, and then we're going to tag it agbell demo4. We can build this. So we're actually building a Docker container that we're later going to use to build a Docker container, which I think is kind of interesting, you know, recursion, C recursion. And then once we have this, then we can use it. So how the ikfile works is it has, you know, all the steps you might expect of a parser. So it has steps to convert from a kind of standard Docker file format to LLB. It has some kind of parsing commands and etc. And I didn't actually build this in entirety. What I did is I started with the existing Docker file front end. I extracted it from the Moby project, and then I made some changes to it. And the main changes I made to it was based on this programming language called Intercal. So Intercal is this programming language from the 70s that was kind of made as a joke. It was made to look like Fortran, but kind of in silly ways. So in Intercal, you have to say, instead of just saying 2 + 2, you have to say, please, 2 + 2. So one thing I've done is I've changed the run command in a Docker file to be please, which I feel is much more polite. And also changed some other things. So instead of copy, you can say stash, which is another keyword from Intercal. And to start an entry point, you know, you do please do, and etc. But it looks like we have it built now. So let's see what we can do with it. So this is our ikfile. I'm calling it an ikfile because that the Intercal compiler was called ik, and yeah, I'm just stealing a lot of naming stuff from them. So Intercal had the great innovation of the come from operation, which was the reverse of go to. So if you recall, there was some sort of essay written called "Go-tos considered harmful." So these guys created a come from argument, which is it's like go-to but worse because you're going in the reverse direction. Anyways, in a NIC file, instead of saying from, you say come from. Instead of a copy, you have stash and etc. So now that we have this and we've built our demo 4, we can just use this as our new syntactical front end. So to do that, we'll do docker build. We'll pass it as a file, our IC file. Yeah, our IC file. And then we're going to tag it agbel demo 5. And now we've just built something using keywords that Docker itself does not support, right? We are using a please command and a stash command and a come from, which I think is pretty cool. And then let's run this. Sudo docker run it agbel demo 5. Then we start our shell. And then if we look inside of our build, you can see custom make file built front end. So there we go. We built a custom front end. We put that into a Docker image, and then we use that Docker image to build things using our new syntax. Kind of neat. So I think all this is pretty neat. We started with an interesting question about how containers are actually created, and now I can answer it. And now I've built my own front end. And I can also create my own backends for containerization. These are just proofs of concept, but you can actually do really neat things with this ability. Something you could do is build your own AWS Lambda clone. Using the programmatic functionality that I showed earlier, you could easily build a service that takes in a JavaScript function via a post request, and then programmatically calls buildkit to create a Docker container, throws that JavaScript in it, ships it off to Kubernetes. That might not be that hard, right? Proof of concept of that, maybe a couple hundred lines of code. Another thing you could do is just build a specific image format for your org. This one here is called Mocker file, created by somebody online. The creator noted that the Docker files in his organization, they were mainly just a list of a whole bunch of things that you needed to call apt get on. And you could do them on a per line basis, but that generates a layer per line. So instead, people just end up jamming them all onto a single line. And that's kind of unideal, right? It's just kind of a mess. So in the Mocker file format, which is specified in YAML, you just provide a list of packages, and the Mocker file will send the LLB to install all those into a single layer. For this specific use case, it's kind of the best of both worlds, right? You have cleaner code, it's less prone to errors or duplication. And I don't know, the Mocker file is specified in YAML, which isn't always the best tool for the job, but I think it works really nice in this case. The other thing is just there's much more to learn here. I know how front ends works now, and we kind of showed some of that, but we haven't even explored the middle and the back end. There's a lot that can be done here. Like, what could you build with this ability? That's my big message. Like, what could we create with this? We won't actually know until we do. When LLVM was first created, it was for making a C and C++ backend. Rust didn't exist. Swift didn't exist. There was no pixel shader backends or WebAssembly. Now we have these tools for creating cloud native workflows. So what should we do with that? I work on this project Earthly, and we use some of the build kit features to pretty neat effect, but it's kind of a playground that's available here for anybody. What can you build on this? On a historical scale, I think we're super early in terms of cloud computing. So I want to see other people use this to build something cool. And that's kind of my big message. Go out there and build something. And if you do, let me know. I'm Adam Gordon Bell. Thank you so much. I'll share the links to the source if you want to play around with this. And yeah, if you build something, let me know. And if you're looking for inspiration, obviously check out Earthly. I think it's pretty cool. Thank you so much for watching my talk.